Welcome to my video course on mastering ERTMS/ETCS signaling systems, where today we will bridge the physical track infrastructure with its abstract digital data encoding. We're going to dive right into the incredible engineering that allows tracks and trains to communicate seamlessly. It's this exact technology that guarantees absolute safety and interoperability across modern, high-speed railway networks. So let's take a quick look at our agenda for today. We'll kick things off with an introduction to Eurobalises. Then we'll break down the differences between fixed and switchable variants. After that, we'll cover how Balise groups manage transitions, look at the overall ERTMS/ETCS telegram structure, and finally, decode everything by looking at variables, packets, and messages. All right, let's jump straight into Section 1, Introduction to Eurobalises, the physical track-to-train interface. We have to start with the absolute foundation of track-to-train communication, especially when we're dealing with environments that don't have traditional lateral signals. I'm talking, of course, about the Eurobalise. This is a vital piece of equipment bolted right to the center of the track, and its whole job is to transmit safety-related information to a train's onboard computer the exact millisecond it passes over. But you know what's really fascinating about this air-gap interface? The Trackside Eurobalise is entirely passive. It literally has no continuous power supply of its own. Instead, the train's onboard unit uses its antenna to beam a telepowering signal down to the track. This sudden burst of energy wakes the Balise up, allowing it to instantly fire back its uplink data to the train. It's just a wonderfully elegant and reliable system. Moving right along to Section 2, Fixed versus Switchable Balises and how we classify these track magnets. So, depending on what a specific stretch of track actually needs, the network relies on two distinct classifications of these magnets. First up is the fixed Balise. This piece of equipment transmits a constant, predefined message that is permanently stored right in its internal memory. You can think of it like a highly precise electronic milestone. As a train travels along, its onboard sensors are constantly calculating speed and estimating distance, but as you might guess, those estimates can drift slightly over time. The fixed Balise acts as a trusted reference point for location management, instantly correcting any distance measurement errors the onboard computers might have accumulated. On the flip side, we have the switchable Balise. This one is highly dynamic. It can transmit variable, changing messages based on real-time info it gets from a device called the Line-Side Electronic Unit, or LEU. You'll typically find a switchable Balise installed near physical signals. Its main job is to hand the passing train an up-to-date movement authority, which is basically a digital green light to proceed, based entirely on the current status of that specific trackside signal or interlocking system. Seeing them side by side really highlights the contrast here. The fixed Balise gives us that unchanging geographical anchor. It's basically shouting to the train, "You are exactly here." Meanwhile, the switchable Balise is a live, dynamic gateway linked to the whole signaling network, telling the train, hey, based on traffic ahead, here's exactly how far and how fast you can go right now. We absolutely need both for a safe, fully functioning network. Let's get into Section 3. Balise groups and transitions, and how we deliver complex data. Sometimes the safety data needed for a location is just way too complex or voluminous for one single track magnet to handle in the fraction of a second a high-speed train flies over it. And that is exactly where Balise groups come in. By placing multiple Balises in a sequence, they combine forces to handle these heavy-duty tasks, providing complex operational data and ultra-precise positioning. One of their biggest jobs is safely managing transition announcements. For example, they're used to alert a train that it's approaching a fully supervised ETCS Level 2 area, a zone where physical trackside signals might not even exist. The Balise group broadcasts exactly how much distance is left before entering that zone, so the driver and the computer can safely prep for the transition. Now for Section 4, the ERTSS/ETCS telegram structure, which is our digital payload. Now that we're firmly grounded in the physical infrastructure bolted to the tracks, let's shift gears to the digital payload itself, the telegram that the air-gap interface transmits to the train. To make this data structure a bit more intuitive, I want you to think of the ERTMS/ETCS syntax exactly like a spoken language. Variables are your individual letters or words, packets are the phrases grouping those words together, and messages or telegrams form the complete actionable sentences that the train's computer actually reads and executes. And that brings us to Section 5, Variables, Packets, and Messages. Let's decode this language. Let's break down each tier of this coding hierarchy so we can see exactly how this vital safety info is bundled up. Starting at the base level, we have variables. These are the absolute foundation of the whole encoding system. They hold single, unsplittable data values pointing to a very specific, unambiguous track entity. For instance, a single variable might transmit the unique ID number of an upcoming level crossing. It's a precise, atomic unit of info that the computer can instantly parse with zero ambiguity. Building up from there, we group multiple variables into a defined internal structure called a packet. And every single packet leads with a critical header containing structural info. It dictates the NIDC packet, which is the unique identifier so the computer knows exactly what type of data is incoming. Then we have the QDIR, dictating the validity direction, like does this rule apply to trains moving in the nominal direction or in reverse? And finally, the L packet strictly defines the total bit length of the packet, ensuring the system knows exactly when the phrase ends. Finally, all these packets and individual variables get assembled from top to bottom into complete messages, also known as telegrams. This is the top-level data structure. Much like a highly formalized sentence, it contains a message header, plus a predefined set of variables and packets. A perfect example of a message would be an SR authorization or a full movement authority. These messages provide the overarching command and control logic, feeding the onboard computer everything it needs to generate a safe braking curve and monitor the entire journey. So when you really think about it, by understanding both the physical Balise and its strict digital language, we are securing the interoperability and the safety of the entire network. The seamless operation of modern railways relies 100% on every train interpreting this exact same language, from the physical energy burst of the air-gap interface right down to the logical parsing of packets and messages. Mastering this architecture is what allows trains to cross borders without ever compromising on safety. Thanks, we can see you next video.